Hello class and welcome to section 8.3. Today we're going to look at graphing rational functions. Since we will be graphing, you're going to want to have your graphing calculator handy. And if you do not have a graphing calculator and you're in class, feel free to pause the video and come and get one from me. Otherwise, just make sure you have it ready to go. So, graphing rational functions. Let's look at the example or the other functions that we have graphed so far this year. The first one that we have graphed is a linear function. Okay, remember to be linear. It looks like y equals mx plus b. Biggest thing to notice is that this one is my x is to the first power. So if I have an x to the first power, that means it is linear. Okay. Another function we've graphed is the quadratic. Y equals ax squared plus bx plus c. Biggest thing that lets me know that this one's quadratic is if I have an x squared term. Okay. The next one we've graphed is a square root function. And that's y equals the square root of x. So in order to be a square root function, you have that square root. Remember, it always takes the shape, has a starting point, and then it kind of curves and goes up. Some other polynomials that we have talked about is this one would be, there's two changes in direction, so 2 plus 1 is 3. So this is a third degree, so it means it's a cubic, so it has an x to the third in it at some point. This one has 1, 2, 3 changes in direction, so 3 plus 1 is 4, so this one is a x to the fourth, and this one we have 1, 2, 3, 4 plus 1, so this is a fifth degree polynomial. So it's an x to the fifth. So today we're going to go ahead and graph rational functions, so functions that have been written as fractions. Okay. Before we do that, let's go ahead and just look at an example that's already graphed for us. A group of teachers want to get their favorite teacher, Mr. Domingos, a birthday gift. They plan to get him a gift certificate for a weekend package at a lodge in a state park. Okay, the gift certificate costs $150. If C represents the cost for each student and S represents the number of students, then, okay, well, what's the function we're working with? Okay, so if I want to figure out the cost per student, so it's dollar, we want to figure out the dollar per student. The amount of money is $150. Divided by the number of students, which is S. So my function is 150 over S. Okay. Well, let's think about it. If there's one student, okay, that means they're going to pay, that one person is going to pay $150. Okay, so if I graph this, I have 150. If I have two students, that means they're each going to pay $75. So here's my 275. If I jump up, if there's 25 students, 150 divided by 25 will give me 6, so that means they'll each pay $6. Okay, so there's that ordered pair here. So this is an example of a part of a rational function. Here's my example of my rational function. Biggest thing to take note of is that my denominator, which is S, you cannot have your denominator equal to 0. Okay, so what's happening here is there is an asymptote, which makes sense in terms of the money situation because if there's 0 students, okay, you can't take $150 and divide it by 0 students. There's no dividing that can be done there. So there's an asymptote there. Okay, so it'll get really close to 0, but it won't actually touch. Same thing with my y value, my y-axis. There's an asymptote here. This will get really, really close to that y-axis, but it will never actually touch. Okay, so let's go ahead and look at what is a rational function. Okay, we've talked about this already, but it's a ratio of two polynomial functions. So I have listed here some examples of rational functions. The next thing we need to talk about is continuity. Okay, another thing about continuity is if a function is continuous or not. That's where continuity comes from. So the graphs of rational functions may have breaks in continuity. You won't be able to trace the graph without picking your pencil. So to be continuous, to be a continuous function, okay, let's just draw. I'm going to have an x to the fourth function. Maybe if I can draw some nice. Actually, let's do an x to the third. If I have something like this, okay, I do not need to pick up my pencil at all as I draw this. So my x to the third or degree 3 polynomials, those are continuous. Okay, rational functions, though, they're going to have breaks. Those breaks will typically be asymptotes. Okay, so in those asymptotes, there is a break, and I will have, like if this is my rational function, see how I had to pick up my pencil to get to this other piece? That means it is not continuous. Okay, so breaks occur at values that exclude from the domain. The places that are excluded from your domain are where your denominator is equal to 0. So keep that in mind. Okay, so where denominator equals 0. So let's go ahead and just look at the examples from above. If I'm looking at f of x, where would f of x not be continuous? Okay, well, I would have, in my denominator, I have x plus 3, so I set it equal to 0. So at x equals -3, it is discontinuous. Okay, so this means that what's happening here, that there is a vertical asymptote, which I drew here in the pink. So there's a vertical asymptote. If I move ahead and look at my g of x function, okay, so for g of x, it's really x minus 6 equals 0. So if I set that one equal, I would get that x equals 6. So at x equals 6, I have a vertical asymptote for this one, right? The next one, h of x, okay? There's a little bit more to deal with h of x here, and I'm going to rewrite it. So h of x, so we have x plus 4 all over x minus 1, x plus 4. All right, this one, I would set each piece of my denominator equal to 0. Okay, but here's the thing. Do you guys see how the x plus 4s would cancel? If it cancels, that is where there's a hole. That means that there's a hole. So in order to figure out where the hole is, I would say x plus 4 is equal to 0. So my hole is at x equals -4. And the way you would draw a hole on a graph would be drawing an open circle, like I did right here. So there's a hole there, and then at my other piece that's left alone, that's where my vertical asymptote is. So if I take x minus 1 equals 0, I get that x equals 1, and that's a vertical asymptote. Okay. We're going to talk about those things just a little more on the next slide. So, vertical asymptote. It's a line that the graph of the function approaches but never touches due to domain restrictions. And my domain restrictions, remember, come from my denominator. Okay? So in this case, we have the x minus 3, and I would say, well, x minus 3 equals 0. So at x equals 3, I would graph my vertical asymptote. There it is. Okay, and it came from my denominator. So at x equals 3. The next one, the point discontinuities, the hole in the graph. We've already kind of talked about this above. Okay, but holes occur when you have a value excluded from the domain, but cancels out when the function is simplified. That canceling out tells me it's a hole. So if I'm looking at my function here, if you notice, the x plus 2's will cancel. So the hole is when x plus 2 is equal to 0. So x is equal to -2. Okay. If you want to figure out what the y value would be, see how these are canceled out? You're going to plug in your hole, -2, into what's left. So it'd just be -2 minus 1, because that's the piece that's left. So at -3. So my hole is really happening at the ordered pair -2, -3. And see how it's drawn there with an open circle. Okay, so that's how you would figure out where your hole is graphed. All right, if you need more time to write down anything on here, please feel free to pause the video so that you have all the stuff that's written here on your note sheet. So, throughout all these problems, just to continue to keep in mind that you can't have a denominator of 0. Okay, so we have a fill in the blank on your note sheet. No denominator in a rational function can be 0 because a division by 0 is not defined. Okay, and you're going to hear words that ask for, well, find where it is undefined. And to figure out where it's undefined, you take your denominator and set it equal to 0 and solve. Okay, so it's setting it equal to 0. Because you're going to have some problems on your upcoming quiz that talks about undefined. All right, so example 1, let's look at this. Determine the equation of any vertical asymptotes and the x values for any holes in the graph. Okay, so the first step, you want to factor both the numerator and the denominator if possible. So if I look at f of x, my numerator has a difference of perfect squares. So I'm going to have x plus 1 and x minus 1. All over my denominator, need to factor that. So what multiplies to 5 but adds to negative 6? Well, negative 5 and negative 1, that multiplies to 5 but adds to negative 6. So I look, okay, does anything cancel here? My x minus 1's cancel. So if it cancels, so it canceled out. If it cancels, that makes it a whole, okay? So x minus 1 equals 0, so at x equals 1, that is our whole. If I wanted to know where to graph the whole, I would take it and plug it into what did not cancel out. So you would do f of 1, which would be 1 plus 1 over 1 minus 5. So this gives me 2 over negative 4. So it gives me negative 1/2. So graphically, I would have a whole at 1, negative 1/2. Notice my directions will only ask for the x value. So you'd only have to tell me this, but if you were graphing, you'd want to plot this point and put a whole there. Okay, so there is my whole. Now let's go ahead and look at the vertical asymptote. The vertical asymptote comes from setting the other piece in the denominator equal to 0. So my vertical asymptote is my VA, so I would have x minus 5 equals 0, so x would equal 5. This is my vertical asymptote. Okay, so remember, what cancels out, that's where your whole comes from. What's left after you do the canceling, that is where your vertical asymptote is. All right, example 2, same thing. Determine the equation of any vertical asymptotes and the x values for any holes in the graph. So let's go ahead and factor this one. So what multiplies to 8 but adds to 6? 2 times 4? That would work. And then my bottom is a difference of perfect squares, so I have x minus 4, x plus 4. Now I look, does anything cancel? The x plus 4's cancel. So the whole comes from x plus 4 equals 0. So my whole occurs at x equals negative 4. So this would be my answer for my whole. But remember, graphically, just to get some practice, we would plug it into what's left here. So it's really x plus 2 over x minus 4. So if I wanted to figure out the y value, so I plug in negative 4 to what's left. So it'd be negative 4 plus 2 over negative 4 minus 4. So this would give me negative 2 over negative 8, so at 1/4. So my whole, if I were to graph it, once again, would be the ordered pair negative 4 and 1/4. Okay. Then my vertical asymptote comes from what's left. Okay, either here or here, doesn't matter. So my vertical asymptote is when x minus 4 is equal to 0. So at x equals 4, I have a vertical asymptote. So then my whole and my vertical asymptote. All right, example 3. So I'm going to determine the equation of any vertical asymptotes again, and also any holes. So let's go ahead and factor. My numerator would be x plus 2, x minus 2 because it's that difference of perfect squares. Then I would say to myself, what multiplies to 6 but adds to 5, plus 2 and 3. Here I notice my x plus 2's cancel, so my whole comes from when I take x plus 2 and set it equal to 0. So my whole occurs at x equals negative 2. Once again, just a reminder, if I wanted to figure out what my value would be graphically, where I would draw the open circle, I plug it into what is left. So I would do f of negative 2 is equal to negative 2 minus 2 over negative 2 plus 3. So I would have negative 4 over 1, so at negative 4. So my ordered pair for where I would draw that open circle would be negative 2, negative 4. And then my last thing is to find my vertical asymptote, and that comes from what does not cancel out. So it's that x plus 3. So my vertical asymptote is when I take x plus 3 and set it equal to 0. So my vertical asymptote occurs at x equals negative 3. Okay. I think this is a good stopping point for the first part of the video. We'll actually get into the graphing when you guys come back for a part 2. So take a little break. Sorry you didn't need your calculator I guess, for this piece, but we will be using our calculator for examples 4 through 7 on the note sheet. So please pause the video, take a break. If you have any questions on this, write it down, come and ask. Otherwise, come back ready with a graphing calculator for part 2. All right, have a good day, and I'll see you in a bit.